This is BB Lake. So if water is, or this flowing water down there from the falls is like electrical current, then this water right here, this small lake above the dam, is basically like the voltage source, the potential source that will cause the water to move, just like voltage forces electricity or electrical current to flow in the form of charged particles. All right, so here is our voltage supply, complete with geese. By the way, I came across 2 geese, roughly 18 goslings. Didn't know they had groups that large. They hissed a lot. They were afraid we were going to go after the goslings. But the problem is Max just wanted to pet one, so I guess he was part of the problem. Bye.
What we're going to do is use these clips and the analogy of Fall Creek going away from BB Lake as a waterfall analogy for an electrical circuit. As we go through, I'll say, all right, this represents this component, this is why, and this is what it would look like in a circuit. We're just kind of building our way through. Now, that video clip from BB Lake, I was standing right about here over at the lakeshore, all right, and the water up here, again, it's like a potential energy source. Gravity wants it to flow down, so this is our source. And the waterfall, the size of the waterfall is kind of like a way of measuring our source. And our source in an electrical system is a battery or a voltage source, and we'd represent it like this. All right, so our waterfall right here, the size of the waterfall tells us the size of the voltage source, the size of the battery. Current is flowing over, water current's flowing over, and that's kind of like, electrical current. This is the source of electrical current. This potential drop here gets those charges flowing. Now when charges flow through a battery or from a battery, we consider it like this on the schematic. The long side here is positive, the short side is negative, and it flows from positive towards the negative. That's just how we think of flowing in a circuit. All right, there's our first part.
Now here I am at the falls that run down to the hydroelectric plant. Remember, the energy stored in the water is gravitational energy. It wants to fall down, but it can only fall down so far. So all the energy it has stored up here becomes a different form of energy when it goes over the waterfall. We call that kinetic energy. Anytime you have energy stored in an electrical system used across a resistor, we call that a potential drop, because it actually takes away some of the potential energy of the system. Just like the water can only fall down so far, it can only drop to a certain level through these waterfalls, converting a certain amount of that energy into kinetic. In an electrical system, that potential drop is a decrease in voltage, and there's only so much voltage a system can use. And when the energy does decrease, it becomes something like heat energy in the circuit or light energy in the circuit. But there's a potential drop right there.
Now the very next part of our circuit is pretty straightforward. You can't flow away from a battery if you don't connect with anything. So we're going to consider that blue flow right here of water, right here. And over here, we give a path for the flow in the form of wires. So the wires are going away. All right, so as we connect components on this circuit, we just connect them with straight lines, and those represent our wires going from one place to another. Now, where does that water flow lead to? It leads to a place lower in the rocks, or lower on the stream. And as you can see, there's rocks sticking up, there's a bend in the creek. All these things are going to slow down the flow of water. Anything that slows down that flow of water will be considered something that resists the flow of water. And on our electric diagram, our schematic here, we represent anything that slows the flow of charged particles or electrons as resistors. And these things are going to slow stuff down. And when you slow down current flow, you're taking energy from it and you're converting it to something different. It could be a way of charging your phone. It could be heating up a light bulb, or, if you got like one of those fancy little seat heaters in your car, you actually turn that on, your battery is flowing a current through coils that are in your seat, warming the seat you're sitting in. Either way, anything that slows down the flow of electrical current is a resistor. We'd represent it like this, and since these rocks in this bend in the stream slows down the flow of water, we consider those resistors. So rocks and a bend in the stream slowing stuff down.
Now I'm upriver of that hydroelectric station. It's actually further down around that bend and over another waterfall. Now, one of the reasons you actually have to decrease the amount of water that flows through a hydroelectric power plant is something that I wanted you to experience in person with a hand crank generator that I have at the school. We really just turn a crank like an old fishing rod, and you actually move a generator, a physical generator that creates a current. The thing is, the faster you crank the generator, the higher current you get. But because of the interaction between charged particles moving in a wire and the actual magnets, you get a bit of a backfeed resistance, a physical resistance to the turning that actually decreases the effectiveness of your generator. So if you allow too much water to flow through the generator, you actually make it so it is doing a poorer job of generating electricity.
And once we get past that bend in the stream that's actually slowed down the flow a little bit, and we represent it as our resistors, we get to another feature of the creek. So there's our arrow, there's our extra wire to connect to the next component, and we hit another waterfall. Now this waterfall is smaller than this one, all right? And that's why I gave it a slightly smaller symbol just for you and I. You know, anytime you draw a battery, you don't have to draw the battery, you know, large battery has a large symbol, small battery has a small symbol. No, usually we write the actual voltage there and draw everything all the same. But for the purpose of this, I want you to know the bigger this is, the larger the waterfall, the more voltage, more push, more kinetic energy for the water particles, which means the faster you're going to have your electrical current. So we hit another waterfall right here on the way to the hydroelectric plant. And we connect with wires to the next piece. All right, flowing along, and that's where we get to the actual hydro plant. Now, what is this hydro plant going to do to the flow of water going along here? Is it going to speed it up? Because unless it speeds it up, it can't be anything other than a resistor. Let's take a look.
All right, right now I'm coming to you from Cornell's hydroelectric power plant, and we've had a lot of rain recently, so as you can see, Fall Creek is flowing pretty heavy from BB Lake. Now, this right here is that hydroelectric power plant. We use water, or flowing water, as a great analog for direct current electricity, but how is it we get electricity, several 100,000 kilowatt hours of electricity from this particular power plant? It has a lot to do with all that flowing water you see coming out of it, but the thing is, they actually decrease the amount of water flowing through in times like this when there's a whole lot of flow. So like, why do they do that? Is that a waste? Could they be generating more power, more electricity if they didn't throttle it down? That's one of the questions we're going to have to answer. But hydroelectric power, or hydroelectric generation, is one of the ways we generate current electricity.
Now, I kind of glossed over this, but you may be thinking, is it possible to have more than one battery in an electrical circuit? Absolutely. Last time you maybe changed the remote, the batteries in your remote, you may notice there's batteries, not battery. So depending on how you put your voltage source in the circuit, you kind of add to the overall voltage. And that is not always the case. See, you have to have the flow going the same way for the voltage to add. So remember, it goes from positive long side to negative short side, going around, to positive long side to negative short side. These are pointing the same way, the voltage is going to add. Now, what's the next feature? That's right, that hydroelectric plant itself. The hydroelectric plant actually slows down the water quite a bit as it turns turbines. The turning of the turbines creates an interaction between electrical and magnetic fields that forces charged particles to move. Now, realistically, in a real sense, this is a source of voltage. But considering our water analogy, where things speed up or slow down the flow of water, this is slowing down the flow of water. So for right here, it's like a huge resistor, really slowing things down as they come through, taking energy away. So again, just for the waterfall analogy, this is a giant resistor. After we get past that, we head on to different features. So the water continues down, and our wires continue till we get to the next water feature, which is a huge waterfall called Ithaca Falls, and it leads down into Fall Creek, which goes straight to Hugo Lake. Again, we have a voltage source. It's going positive to negative, positive to negative, positive to negative. It adds to the overall voltage of the system, making current flow in a certain direction. Just like in electrical systems, when we add voltage sources and they go in the same direction, we add to the thing that's pushing current along, achieving some sort of a job in our circuit. All right. Now after that, we hit a whole bunch of resistors, lots of rocks in the stream, until finally you end up in Hugo Lake. And that's kind of the end of our waterfall analogy, unless of course you want to consider the water cycle itself, a nice humid day, you can see the haze, water is evaporating from the surface going back up, and that's kind of like completing our circuit going back up to BB Lake. But there's our waterfall analogy. And this is what a circuit schematic would look like. So, something that forces current along, a voltage source, wires connecting to resistors, things that slow down the flow of electrical current, while taking some of the energy, some of the voltage away from the circuit to do a job, like lighting a light bulb, and then going all the way through. And if you were to add it all up, the voltage provided here will be taken away by these resistors. All right, what's the relationship between that, the voltage and those resistors? Well, that would be current. Remember Ohm's law? So Ohm's law, V equals I times R, voltage equals current times resistance. It's obeyed by each one of these. We could tell based on how much voltage is in the system exactly what the current is going through each one of these resistors, as long as we know how big the resistor is. That's just how circuits work. Our next step is to get into the logic of series and parallel circuits, but that is a different video. I hope you enjoyed that quick tour of Cornell. You really just hop in a car, go down there, take a beautiful walk. I wish I could have taken you there myself. See you later.